All right, so we've been talking about, like I said, sort of chapter 2, electrons, and we really sort of delved into quantum numbers and electron configuration last time. Remember, sort of the quantum numbers are really the sort of basis, if you will, for why we write electron configuration like we do, what orbitals electrons are in, sort of the mathematical or theoretical sort of solving of on each energy level how many orbitals there are, how many subshells, the order at which those electrons go in. So as we talked about, as long as you sort of know the thing up here on the top in terms of how many maximum electrons you could put into a particular orbital or subshell and sort of the order at which they go in, you really should be in pretty good shape in terms of writing any electron configuration. I think we finished up on sort of this slide here, talking about the idea that, you can use the periodic table as, a way to sort of count off electron configuration if you want. The first two groups there are the S block, which is like kind of the light blue there on the left. On the right-hand side there, the yellow, basically groups 3 through 8 are the P block. Our transition metals here in purple are the D block, and then our kind of two guys that are set down on the bottom are really the F block in terms of where electrons go. And remember, though, that we can use the period number as sort of the N number, if you will. So up here would be like 1s1 to, that's what hydrogen would be if you go all the way across, 1s2, and then come down here 2s2 and so forth. Remember, though, that these do not start until the third energy level. So that even though that's on sort of the fourth period, it is actually 3D over here and not 4D, which again is sometimes a common mistake. Also, that happens on the bottom as well. You will see that this row actually goes here, which is really the sixth. This guy's actually 2 behind. There's a couple places where you got to be really careful as you're sort of trying to read off electron configuration. My best advice is probably go with the sort of guy over here on the right, the kind of zigzag thing. That's probably the best way. Probably less room for error as well. So let us continue on. So, oops, oh, I guess we'll just look at this, I suppose. So if we're going to write an electron configuration again for something like sulfur, we always start at the top of that guy and sort of zigzag back and forth, and we would go 1s2, 2s2, 2p6, 3s2, and 3p6. Remember that we also can write sort of a shorthand for electron configuration, which is sometimes referred to as the noble gas configuration. And that is basically we take the noble gas, which is group 8 on the periodic table, and we put it in brackets. So that little neon there represents neon's electron configuration, which basically takes you through here. And then you kind of continue on with the rest of the configuration as well. Barium, which is 56 there, does that same thing. It goes to xenon, which comes right before it, and then does your 6s2. And again, you could also write out all of that there, like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, I think. That takes me to 5p6 and 6s2. So like if I did the math right there up to there, 2, 4, 10, 20, 30, 36, 38, 48, and whatever that comes to there, 34, 54 in that case. And Einsteinium, obviously xenon, and then you kind of continue on with the configuration. Any questions on sort of how to write electron configuration for those guys? We also talked about a little bit about what happens with charges, right? If things do have charges, you do have to adjust the electron configuration. So again, if something has a positive charge, then obviously it lost electrons. So you need to subtract it from the total. And if something has a negative charge, it obviously gained electrons. So you need to add it to the total. So let's talk a little bit then about transition metals and some slightly different things that occur with transition metals in terms of electron configuration. Now, transition metals have, as we saw, basically the D block. So they have incompletely filled D subshells, or they give rise to cations that have incompletely filled D subshells. When we talk about sort of transition metals, which again is that was purple area there that was on the chart, you will be given a periodic table for the quiz. It will be provided for you. All right, so the transition metals, which was in that sort of purple area there on the periodic table, there are that D block. So, they do end up obviously with, especially the first row there, 3D, 4D, 5D, depending on sort of where you are in the transition metals. Now, there are several exceptions to sort of the normal electron configuration that you might have for transition metals. And two very common ones that we talk about are what we see on the bottom, which is chromium and copper. Now, if we look at something like chromium, for example, which is number 24 there, if we just follow the normal sort of zigzag guy that we were talking about, how to write electron configuration, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, you would go 4s2, and 3d4. And this is probably normally how you would write the electron configuration, again, if you followed that zigzag kind of back and forth guy that we've been using. Now, it's been found experimentally that actually chromium and copper are sort of exceptions to sort of normally how they go. And the exception happens actually right here at the end. So at the end, what ends up happening is there's actually an extra electron up in the d orbital and one less electron in the s orbital. And that means that when the electrons go in, they do go in 4s first, as we talked about, and then they follow with 3d. So what ends up happening is we end up with a configuration that looks like this, where basically that s electron from below really got promoted up to the d orbital. And what we create is a really nice sort of situation here, according to Hund's rule, right? We really sort of maximized all the parallel spins, again, just found to be more experimental. You may be asking, so how can that happen? It can happen because really, truthfully, this orbital here and this subshell here, they're really, really close in energy. They're very, very close in energy. So it doesn't take a lot for that electron to be able to sort of promote itself up to the d orbitals. It's able to do that relatively easy. In fact, as we'll talk about in just a second, what actually happens in terms of those orbitals, that they're so close in energy that actually when we start kind of putting electrons up here in the d orbitals, there's actually a switch in energy that occurs, and the 4s actually ends up becoming slightly higher in energy than the d orbitals. So as the electrons go in, the s's are lower in energy than the d's, which is why the s gets them first, as we talked about earlier. But as you start kind of filling those d orbitals, there's sort of a switch that occurs. And that's going to be really important in terms of what happens when transition metals lose electrons, as we'll talk about here in just a second. Copper, pretty much identical sort of exception. Copper, which is 29, pretty much does the exact same sort of thing. Again, if you were to follow that zigzag sort of guy there to get the electron configuration, you would end up with something like this. Same sort of area where we see the exception. Again, that s electron goes upward, and the correct configuration here is what we see on the bottom there, basically 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. And just to be clear, chromium's correct configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So again, and that's pretty much what's on the bottom there. These are the correct sort of electron configuration for chromium and copper. For the most part, those are the two that you most often sort of come across and are usually asked to sort of remember. I will say that there definitely is a lot more exceptions in the transition metal region. Actually, if you look, and we'll see a few here, I think in just a second, but if you look kind of where chromium copper is and kind of go below them on the periodic table, you'll see a lot of sort of elements that do have similar type of exceptions where there's sort of an extra electron up in the d orbital, one less in the s. In fact, there's even one where there's actually no electrons still in the s orbital. They've all been sort of promoted up to the d orbitals. And again, as we talked about, the reason, it's sort of able to happen and not such a sort of big deal in that sense is because, again, they're very, very close in energy. So it doesn't take a lot for those guys to kind of get themselves up there in terms of higher energy and lower energy. So here are, again, some of the exceptions to sort of the normal normal electron configuration. And again, there are very, very similar sort of exceptions that we commonly see. There's our chromium and copper. This is sort of what we would expect to occur, as we talked about sort of the exception happening here. Again, we see a similar exception with MO there, which is right below chromium on the periodic table. Again, an extra electron up in the D, one less in the S, and RU as well, and PD. So those guys, again, if you look on the periodic table, they're all in that sort of area where we have kind of chromium, copper sort of hanging out. Silver as well is another exception, has a similar type of exception. Platinum here, as mentioned before, here you can see actually has no sort of electrons still there in the s orbital. They've been promoted upwards there as well. Any questions on that? For us, I will say that you would be responsible for just chromium copper. For us, you should be aware of the other sort of exceptions, but for the other exceptions, you can just write it like normal. Understand, obviously, again, that they are probably some exceptions and they may not be 100% correct. But for us, I say you do need to know for sure chromium, copper. Those are, again, sort of the most common ones that we come across. Any questions on that there? So how does some of this stuff affect, say, transition metals when they lose electrons? And it has an effect on what happens with them when they do lose electrons. And what happens when they do lose electrons, it's a little bit different than what we refer to as sort of the representative elements. And the representative elements sort of on the periodic table are like those elements sort of on the outside, not really where the transition metals are. So where the transition metals are, we do see some differences that occur in terms of what happens when they actually do sort of lose those electrons. So we just kind of back this up to get some more scribble on here. So for example, again, if we looked at some type of representative element, say like sodium, and even chlorine, for example, just kind of do one of each there. So if we look at sodium, again, it has 11 electrons. When it does become +1 charge, it ends up with 10 electrons. And it really does end up with a configuration 1s2, 2s2, 2p6, where the original was 1s2, 2s2, 2p6, 3s1. It loses that valence electron, as we talked about, basically the last guy that really does sort of come in the configuration. Same thing with chloride, for example. Chloride, again, will actually gain in there. So chlorine, which is 17, 1s2, 2s2, 2p6, 3s2, and 3p. 1, 2, 3, 4, 5 there. It will actually gain the electron there at the end, is where that electron will basically come in, giving you 1s2, 2s2, 2p6, 3s2, 3p6, again, getting it to basically 18, which is argon's configuration, and getting this guy obviously back to neon's configuration. So when we talk about transition metals, they're a little bit different, and it revolves around what I just mentioned a second ago, that when those electrons go in, the orbitals are sort of arranged in this sort of situation in terms of energy. Again, we're going to fill our 4s first and then start filling our 3d. At that point, we do get a switch in sort of the energy levels. And what ends up happening is, as I mentioned a second ago, the 4s actually ends up being higher in energy than the 3d. So when a transition metal, which this occurs for, starts to lose electrons, it is actually going to always pluck off the 4s electrons first. So we lose these first, because they actually do end up being the highest in energy. So they kind of switch, they end up being really the highest in energy. So we do take those off. Now, if something happens and we need to lose more than 2 electrons, clearly you can see in the 4s region there, you only have 2 electrons to lose. At that point, then the next highest would be the Ds. So slightly different, in terms of when they lose electrons. Transition metals doesn't necessarily lose electrons when you write their electron configuration from the very last thing that you wrote, and what you very commonly think about. Does lose it from the 4s, which is technically actually highest in energy, and then continues down. Now, if we look at something, for example, like iron, which is 26, and if we did just its configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and iron there, 2, 4, 6, I believe, 3d6. So when iron loses an electron or 2 and becomes iron 2, it now has 24 electrons. So what ends up happening is, again, even though it's not written in that way, because this is the correct order for filling the atom with electrons, it will lose these 2 electrons first. So we will lose these 2 electrons, and it will leave a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 as its electron configuration, or that is argon 3d6 in terms of that. Now, what happens when iron goes to actually a +3 charge, ends up with 23 electrons. Same thing happens. It will first again lose those 4s electrons, and now needs to lose 1 other electron, which means the next sort of highest in energy after that is the d orbitals, and it would lose it there, giving it a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5 are argon 3d5. So a couple of things with transition metals, as you can see, a little bit different in terms of where those electrons come from, but they always, all transition metals always lose the s electrons before they lose the d electrons, Once they lose the s electrons, if they need to lose more than what is there, then they do dip into the d orbital. The other thing that's different than, say, representative elements like in group 1, group 2, or group 3 is, if you remember when we talked about sort of those guys losing electrons, they actually back up to the noble gas that comes right before them, like what we see here with sodium, right? When sodium loses an electron, it backs up to a noble gas and ends up dead on like neon's configuration, which is, again, as we talked about, isoelectronic with neon. That doesn't happen for transition metals. They don't lose electrons typically and back up to the noble gas that comes before them. They basically still remain in the d orbitals, basically, with those electrons when they do gain a charge. So that's why I was talking about before that transition metals give incompletely filled d subshells when they make cations. They actually don't lose enough to back up to, say, argon, for example. So if you looked at something like iron, which is 26, it would essentially have to lose, was that like 8 electrons to get back to argon, and that would be like a iron with a +8 charge, which doesn't really happen. So they typically don't lose enough electrons to go all the way back to the noble gas configuration in the transition metal region. Any questions on that there? Let me see here. Yeah, so in terms of this method, or what happens in terms of when they lose electrons, this is really specifically only for transition metals. So it's really only for transition metals is where this occurs. So if we kind of look back at that, we have that periodic table, I think, where we started. Maybe. So we're really talking about is really anybody within this purple region. That's the transition metals here. So it's all these guys here that when they go to, everybody in that purple region, pretty much, when they go to lose their electrons, they will always lose these S's first. And then they will dip into the D's if necessary. So it's specifically for those guys right there that we're talking about. What I was talking about, representative elements, like sodium, which is like here. When these guys, which are representative elements, really group 1 and 2 and group 3 aluminum, when these guys lose electrons, they always end up back here, at the noble gases, basically. Transition metals never really lose enough electrons to get back to the noble gases, but they always lose their S's first and then their D's when they go through it and stuff like that. And again, it's because of that sort of switch in energy that, we do see them lose those S's first. And that's why sometimes we'll see, or sometimes you'll see, people write electron configurations sometimes where, you see all the sort of threes together. They'll go like, hey, 3s2, 3p6, 3d6, 4s2, or something like that. And you're like, okay, everything's lined up perfectly. And if you follow that zigzag sort of guy, that is the incorrect way of writing it. And the reason why you sometimes do see people sort of put it all together, almost it looks like it's all in order, is because sometimes people will write electron configuration based on energy, which is sort of what happens after it's completely filled up with electrons. And in that situation, because there's that switch in energy that occurs here that we just talked about, the 3D is actually lower in energy than the 4S. You shouldn't write electron configuration like that. You should write it based on the zigzag thing that we've been talking about, and based on what is sometimes referred to as the filling order, how the electrons go into the atom. You should always write electron configuration like that. And I would say in pretty much every chemistry class you ever take, it's always the filling order as to how we do that and how the electrons go in terms of filling the atom. The 4s is lower in energy than the 3d, which is why when we write the configuration like we did here, the 4s comes before the 3d. You really should never write it in sort of the form of energy. I've only taken one class in my entire career, I think, where we did that, but pretty much everybody does filling order, and you should do filling order here. And what I mean by filling order again is that zigzag kind of guy where we did the 1s to 7s and 2p to 7p and all that, and kind of went back and forth as we filled it. So why don't you try maybe a couple here? Why don't you write the configuration for, let's go nickel with a +4 charge. And why don't we do something like, let's do an Mn with a +2 charge. Nickel's atomic number, in case you don't have a periodic table with you, here is 28. And Mn is 25. So write the correct electron configuration for these ions here. Take a minute or two and see what you come up with. Okay, so let's take a look here and see how we're doing. So just again, to sort of see what's happening, why don't we look at nickel here, again, with no charge, which is 28. So again, nickel with no charge would have an electron configuration. If we just wrote it all out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and nickel there is 3d8. If I did that right, we should have 10, 20, 28. Now, when it has a +4 charge, remember that the plus means that it has lost electrons, and it's lost basically 4 electrons from the neutral guys. So instead of having 28 electrons, he will actually only have 24 electrons in this case. And that means, again, when we go here, unlike representative elements, we don't go to the end guy to take the electrons out, because this is a transition metal. It will lose, again, our first couple of electrons out of here. So we'll lose these guys first. That's only 2 electrons, so we do have 2 more that would need to be lost. Those other 2 would then come out of here. And that's going to then leave us on a proper electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Again, we lost these electrons, so they're gone. We also lost 2 electrons out of that last guy, ends us with a 3d6 in that case. You could also, if you wanted to, again, this first part, 2, 4, 10, 12, 18, that again is still argon, and 3d6. Any questions on that one there? By the way, we also see that this guy ends up being isoelectronic with iron with a +2 charge. They both have the same electron configuration as well. So remember, there are times where multiple things can have the same electron configuration. Again, that being isoelectronic with each other. Any questions on that one there? Yeah, in terms of the answer, if you're asking, it doesn't matter if you kind of do the write the whole thing out or sort of this noble gas configuration. It doesn't really matter unless it specifically says don't use noble gas configuration. So obviously, if it says don't use noble gas configuration, you would want to write the guy on the left. If it doesn't mention it, you could, or anything like that, other than it says write the electron configuration, you could do either one of those sort of guys would be perfectly fine. Other questions on that? Okay, then going to Mn here, which is a 2+. Again, if we just sort of look at the Mn with no charge, that is our 25. So Mn, no charge at 25, going to give us a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5 here. And at this case, with a +2, that's going to take us from 25 down 2 electrons to 23 electrons for that guy. Here in this case, that is 2 less, so we're going to simply take out those 2 right there. Again, they will always be the first ones that are lost. That's going to yield us a 1s2, 2s2, 2p6, 3s2, 3p6, and a 3d5. Also going to give us a argon 3d5, also isoelectronic with iron 3. I just randomly picked those two, and they actually ended up being the same as the guys we had before. So again, when we are talking here about transition metals, they do lose electrons slightly different than sort of everybody else, other metals basically. So the key is, again, always lose the S's. The S's could hold a maximum of 2 electrons, so you're always going to probably be taking out at least 2 electrons from that spot. But again, because transition metals can also have sometimes a fairly high positive charge, you sometimes then need to dig into the D electrons and remove those as well. Any questions on how to write electron configuration for transition metals that have charges, or transition metals in general? No, the noble gas configuration you could do for any, you could really do it for anybody, kind of on the periodic table, metals and non-metals alike. So for example, as we did here, for Cl minus, it ends up at argon, and that would be actually acceptable as sort of the noble gas configuration for that guy. For sodium, when it gains the +1 charge, it ends up at neon, which would be the acceptable one for that. The difference between sort of the representative elements, which again are those guys sort of on the outsides of the periodic tables, not the transition metals, is that when they gain and lose electrons, they pretty much will hit the noble gas exactly. So they become isoelectronic with the noble gas, which means when we write the noble gas configuration for those guys, it's actually just the noble gas is the only thing that's there, because when they gain and lose electrons, that's essentially where they end up, is in group 8 on the periodic table where our noble gases are. They end up dead on those guys. Transition metals, as we've just been talking about, when they lose electrons, they back up, but they never back up to the noble gas and end up exactly at the noble gas configuration. So you usually will have the noble gas plus some other stuff to write with those guys. But anything sort of outside the transition metal, when they gain or lose electrons, will pretty much hit dead on group 8, and you'll just end up basically with the noble gas in brackets, like we did up here on top with argon for Cl minus and neon for Na plus. Other questions on that? So you can use noble gas configuration for something that has a charge. And again, just in the representative area, that's pretty much the entire configuration would be just that noble gas. Other questions on electron configuration there? Okay, so obviously at this point, you should be able to draw electron configuration, I guess you should be able to write electron configuration for everybody. Everybody on the periodic table, both transition metals, representative elements. You should also be able to write the electron configuration for everybody with charges, either positive or negative charges. And obviously you should be able to draw the orbital diagrams, as we talked about, I think, last time as well. All right, so it's time to talk about, I think, now the periodic table. Officially here, maybe. So let's talk a little bit about the periodic table. This is obviously the periodic table we've been looking at. And there's several parts of the periodic table, just to make sure, again, everybody's on the same page. We have our basically representation of all of our elements, as we talked about, as they sort of put it together. They did kind of group everybody based on similar sort of properties. So we do see a lot of similar properties as we kind of go up and down on the periodic table, kind of left to right on the periodic table as well. So let's talk about some important parts of the periodic table. As we go up and down in a column, that is what is referred to as a group. Unless you're really old like me, and people sometimes used to call them a family. I very rarely hear people call them families anymore. Most people call them groups. So groups go basically left to right, and there's several different sort of numbering options when you look at periodic tables, depending on your periodic table that you're looking at. You oftentimes will see a couple of consistencies, sort of like what we see here. You'll sometimes see A's listed next to numbers, sometimes see B's listed next to numbers, sometimes just see numbers like we have at the very bottom here, like 1 through 18 and stuff like that. So for the most part, we use what is usually what is referred to as a representative numbering, and probably every chemistry class you use uses the representative numbering, and that is also really the A numbering. So group 1A is here, group 2A is here, group 3A, 4A, 5A, 6A, 7A, and 8A is the correct sort of numbering to use in this class. And like I said, probably every class that you take in terms of chemistry, everybody usually uses that numbering. And that numbering really does go, left to right. We do skip the transition metal region, so no real numbering usually associated with those guys. And then we also, in most cases, kind of drop the A part of the numbering. So, most people will just go, hey, this is group 1, this is group 2, this is group 3, group 4, group 5, group 6, group 7, and group 8. So, when I say group 8, I'm talking about group 8, really 8A, which is really 18. And it's these guys at the end. When I say group 3, it's really 3A and 13 that comes here. So most people just go 1 through 8. Again, also, as I mentioned, skipping the transition metals. Also, really important note is group 1 coming down here starts with actually lithium. Lithium is group 1. Hydrogen, even though it's pretty much sitting there on every single periodic table you ever see, is actually not part of group 1. So it's there for a special reason, because hydrogen has a lot of special sort of properties to it, but it's actually not part of group 1. And that's an important thing to remember. Group 1 starts with lithium, and then sodium, potassium, and so forth. Years ago, on really old periodic tables, they would actually put hydrogen on both sides, left-hand side and right-hand side. You would find hydrogen actually over here as well in some periodic tables. Another important aspect of the periodic table, obviously, besides groups, is periods. Periods run left to right on the periodic table, and we talked about it there the other day, or yesterday, or last week, I guess. It goes 1 through 7 in terms of the periods. Remember, that basically is our N number. But going left to right are periods. So periods are heading in this direction on the periodic table as you go across. Now, so we have 1s, 2 as we were doing the sort of electron configuration. Again, period 1 going across, period 2, and so forth. The number above the symbol, as we've talked about before, that is the atomic number that you find there on the periodic table. The atomic number, right, being the number of protons that there are. Remember that the number of protons is the atomic number, which is on the periodic table. Remember that the number on the bottom there is not the mass number. That, again, is the atomic mass, not the mass number. Now, when we look at the periodic table, it is broken up into a few different sort of regions, if you will. There are metals, non-metals, and what are sometimes referred to as semi-metals, or metalloids. And pretty much on most periodic tables, you can find sort of what is sometimes referred to as like a staircase. And usually it's right around here where boron's hanging out. And we go kind of down like a staircase, working our way down. Everybody pretty much to the left there of that staircase is considered a metal. So everybody to the left is a metal. Pretty much everybody to the right and up of the staircase is a non-metal. And our metalloids are pretty much within this staircase is what we have here. Now, a second ago, we talked about the idea that hydrogen is not part of group 1. And that is because if you look at sort of the coloring here, this is hydrogen. It is actually a non-metal. which means it's actually like one of these guys over here. Again, it's placed over there for certain reasons, but it's actually a non-metal, and that is why when we talk about group one, it does start with lithium group one, um, and down, and hydrogen, even though it's sitting there on the periodic table, is not part of group one for sure. Now, metals are good conductors of heat and electricity. They're malleable. You can hammer them into sheets. You can pull them into wires. They typically have a shiny appearance. Pretty much all metals will be solid at room temperature. The one exception is our good friend over here, mercury. It is a liquid at room temperature, and that's why also sometimes on periodic tables, when you look at sort of the coloring of the symbols, most of the time all of the metals are in like a sort of black font, if you will. The mercury is usually in some other type of color, like blue or purple, to sort of distinguish that. In most cases, mercury is usually a liquid at room temperature. Pretty much everybody else will be a sort of solid at room temperature. Now, nonmetals, on the other hand, pretty much are your opposite of that. They have pretty much opposite sort of characteristics, as you could kind of imagine. Um, than are metals. They are pretty much bad conductors of heat and electricity. They also are dull and brittle, and they also have a more variety of different states in which they come in. So again, our metals are pretty much solid except for mercury. But with nonmetals, you really do get a wide variety of sort of different sort of characteristics, if you will, or states. For example, nitrogen, oxygen, chlorine are gases. Bromine's a liquid. Carbon and sulfur are solids. So they do come in a wide variety of sort of states. And as I mentioned before, again, our hydrogen over here being a non-metal, different than our lithium, that is a metal right below it. And remember that for the most part, a good majority of elements, when you have elements sort of off the periodic table, they come as sort of what are referred to as monoatomic, which means they come as ones. So if you had like a piece of iron, it would just be Fe in terms of the symbol. If you had a piece of copper, it would be just Cu. By the way, they would not have charges. So just so we're clear, since we were talking about stuff with charges, if you said, hey, you had a solid piece of copper, it would be Cu, no charge. Things only really do gain charges when they start to interact with like metals and non-metals coming together, is that's really when things pick up charges. But if they're all by themselves, they really don't have charges. Now, there are several sort of elements from the periodic table that do come as molecules. And remember, a molecule basically is um, the combination of two or more atoms together. And there are some elements that come as diatomic molecules, and most of those are nonmetals. So when we talk about having hydrogen by itself, it's hydrogen gas, H2. When we talk about nitrogen, it's N2. Oxygen is O2, Cl2, I2, F2, Br2. So these guys are, again, diatomic molecules because they basically come as twos. So you got two hydrogens together again, two nitrogens together, and so forth. But this is also elemental form, how they come when they're uncombined. So you never have just like hydrogen gas is just an H. It's never by itself. It's always two H's together to make hydrogen gas. And that's just naturally how they come. And like I mentioned before, hydrogen being a non-metal over there, again, years ago, like I said, on older periodic tables, you would actually see hydrogen kind of on both sides. They very rarely print periodic tables like that anymore. They kind of take it out of the spot. So here's an overlay of sort of our metalloids, which are also sometimes referred to as semi-metals. And you can kind of imagine, we're going from kind of metals on the left-hand side to non-metals on the upper right. So this sort of staircase, and some books include boron as part of it, as you can see in this periodic table, sort of included as part of it. I think your book might as well. Um, but as we kind of go from metals to non-metals here, um, these guys, I don't want to say they're not really transition metals, because transition metals are obviously over here, but they're transitioning from metals to non-metals in the sense of semi-metals or metalloids. They have properties that fall basically on both sides of that sort of staircase. So the same element will have some properties that are very similar to metal properties, while that same element will also have some characteristics that are very similar to what you see in non-metals. So there's sort of a mixture, if you will, of what's on either side of them, metals and non-metals. So they have this sort of mixture of properties and characteristics that you find. And again, the same element will have some properties that are very much like what we see in metals, and the same guy will also have some that are very much like what we see in non-metals, which is why there's sometimes semiconductors are found in that region, because they have some of those similar sort of properties of those two things. Now, there are certain groups on the periodic table which have special names, and you should be familiar with those. Again, group one over here is our alkali metals, and as you can see here very clearly, group one, starting with lithium, hydrogen not part of it, is our alkali metals. Group number two right next door is our alkaline earth metals, and you may be familiar with this word or not, but alkaline pretty much means basic. And when we look at the alkali metals and we look at the alkaline earth metals, and you think about strong bases, for example, some strong bases like sodium hydroxide, potassium hydroxide, most of the strong bases that we sort of encounter actually do come from group one and group two, kind of like this move right here, kind of heading down in that direction. Is typically where we see a lot of guys when they combine it with hydroxide, where a lot of our strong bases come from, and hence why the name are alkali metals and alkaline earth metals, as pretty much alkali kind of means basic. So that's where a lot of bases really do come from. If we go all the way across over here to group seven, that is our halogen. So that's our fluorine, chlorine, bromine, iodine. That's where we find a lot of those diatomic molecules basically happening, like F2, Cl2, Br2, I2, sort of happening here in group seven. Right next door is our noble gases, which we talked a little bit about. Noble gases are group number 8 on the periodic table. Noble gases are really important. They are chemically inert, and as we saw with sort of electron configuration and stuff like that, they are essentially what everybody is trying to achieve in terms of electron configuration. As I might have mentioned, I think the other day as well, it really is the basis of it's really the basis of bonding, and why bonding occurs is to get everybody to that noble gas configuration. Why is that important? It's important because they're extremely stable. So it's sort of a way everybody can kind of achieve that stability. And again, in certain cases, as we'll talk about, when we talk about bonding, certain cases that's achieved by losing and gaining electrons, which is how we get things with charges, or that is sometimes achieved by just simply we're going to share electrons. And that also gets everybody, it's kind of that noble gas sort of configuration. Now, a couple other elements of the periodic table. We have the two rows on the bottom, which is the lanthanides and actinides. And again, if we follow the atomic numbers, we go 57 to 72, but really this 58 sort of period here should end up right there. And 90 would actually end up right after this guy, which is why they're called the lanthanides and actinides, because those are pretty much the elements where they should follow on the periodic table. They are also sometimes referred to as inner transition metals because they technically go there. And that's because the transition metals, as we talked a little about just a second ago, are basically contained between group 2 and group 3 on the periodic table. This row right here is what is sometimes referred to as the first row transition metals, second row transition metals, and so forth. Remember, the transition metals are where 3D orbitals start, right? And down 4D, 5D, and so forth. So these guys on the bottom are sometimes referred to as inner transition metals. These two guys on the bottom here. Again, transition metals pretty much within this region here, the periodic table. And as we talked about, some slightly different things, right? Our S's are lost first in terms of electrons. Any questions on periodic table? So obviously you do need to know the different parts of the periodic table. You need to know obviously which way groups go, which way periods go, the correct numbering. So the representative numbering 1, 2, skip the metal, 3, 4, 5, 6, 7, 8. You need to know where the alkaline metals are, alkaline earth metals, halogens, and noble gases, and where the transition metals are located. Any questions on any of that stuff there? Okay, so what we're going to talk about now are some periodic trends. So we're going to talk about some periodic trends, and it will account for why we see certain things occur when we think about things in terms of why they gain electrons, why certain elements will lose electrons. So we're going to talk about 3 things, or a few more than 3 things. We'll also add probably to this list here electronegativity. And electronegativity is basically really from chapter 3. It's really the only thing from chapter 3 that you'll need to know for the first exam. And we'll get into more about electronegativity in the chapter 3, but just the general trend we'll talk about as well. So one important sort of idea, in terms of periodic trends and why things perhaps lose electrons and don't lose electrons, is sort of an idea, for example, of what is sometimes referred to as effective nuclear charge, and sometimes referred to as Z effective. An effective nuclear charge is really the sort of charge, or the positive charge, an electron feels due to shielding. So you may be asking, what is sort of shielding, if you will. So let's just take an example of something. Let's just look at lithium, for example. We do lithium has 3 electrons basically, and a configuration 1s2, 2s1. There we go. And remember, as we talked about before, these are the valence electrons, right? Remember, the valence electrons are the highest in energy electrons, the one furthest away from the nucleus, as opposed to these lower energy ones, which are referred to as core electrons, right? So when we look at something like, say, lithium, it has basically 3 protons, which means if we think about its nucleus, it's basically got a +3 charge sort of happening there at the nucleus. We have basically 2 electrons, and I'll just draw it like this for this purpose. 2 electrons in the first energy level, right? N equals 1. We then have our 1 valence electron out there in our second energy level, and for our total sort of 3 electrons. Now, when we think about sort of the hold, if you will, in terms of what's happening with these electrons, is when we think about sort of our core electrons, which are these guys that are closer to the nucleus, right? So these are core electrons here. These guys are pretty much like right up in front, right? They're very close to the nucleus. They're pretty much holding or feeling that N is 1, N equals 2. They're feeling that full brunt of that +3 charge. One thing about positive and negative charges, right? We have that electrostatic attraction between positive and negative charges. And it actually, the strength of it, the strength of electrostatic attraction increases with charge. So when these electrons feel that +3 charge, that's a pretty strong attractive force to kind of hold those guys together. So you may be tempted to think, well, obviously this electron here and the second energy level, our valence electron, would be feeling the same sort of attraction. And that's actually not the case. What ends up happening is that sort of third electron here in the terms of lithium is actually shielded from the full brunt of that +3 charge from these two electrons. They're sort of in the way, if you will. So it's kind of like when you watch like a movie or go to a movie theater, right? And years ago, you could pick your own seat, I think. You could get there early, you get like your dead center seat, nobody in front of you, you're really happy. And then, like, right before the movie starts, somebody with a giant hat comes and sits in front of you, just shielded half the screen from you, right? And you can't really see everything and stuff like that. So the same sort of effect happens with electrons that are sort of lower in energy, sort of those core electrons. They really feel that full brunt of that positive charge of the nucleus, while those outer electrons aren't really feeling that. They're sort of partially blocked from that +3 charge. And you could calculate sort of the charge that, say, this electron out here is feeling by calculating the Z effective. We basically take the positive charge of the nucleus and then we add it to how many electrons are shielding. So -1 and -1 is -2. And that electron out here is actually only feeling kind of a +1 attraction. So remember that the strength of that positive negative attraction is based on the charge of it. So the larger the charge, sort of the stronger it's going to be held together. So in comparison, when we look at the valence electron, which is further out, it's only feeling like a +1 attraction. So it's like, okay, I'm kind of attracted there to the nucleus, as opposed to those core electrons, which are feeling the full brunt of that +3 charge. So they're very much attracted to the nucleus. That is also why when we think about when things go through bonding and stuff like that, it is these valence electrons that are involved, because one aspect of it is they're not held as tightly. They're not feeling as strong of a positive attraction to the nucleus. So they're hanging in there, but you can't convince them to sort of leave or even share in certain cases. And you could not really have that happen with our core electrons, which are really close to the nucleus. You can't really convince them to sort of leave because of that really strong attractive force. The general trend in terms of effective nuclear charge is essentially it increases as we go this way on the periodic table and sort of decreases as we go left and down on the periodic table. And that does make sense about some things that we know about. If we go kind of to the right and up on the periodic table, those are typically our nonmetals, which typically gain electrons. Left and down is typically metals, which will lose electrons. So we have this sort of nice trend that occurs. Any questions on that? All right, so let's talk about some of these other sort of important trends. The next sort of important trend is one which is referred to as ionization energy. And ionization energy is the energy that's required to remove an electron from the gas phase of an atom. So if we think about when we remove an electron, right, that is typically when we make a cation, right? So when we talk about ionization energy, we're really talking about sort of the formation of a cation, or a positively charged guy. It's going to lose electrons. Now, one thing that you should be familiar with is electrons actually do come off one at a time. So when something loses electrons, it will typically come off basically one electron at a time. So when we look at something like magnesium, Magnesium, when it loses its first electron, requires about 735 kilojoules of energy. This is what is sometimes referred to as the first ionization energy. It's basically the energy to pluck off that first electron. What then will happen is the magnesium with a +1 charge will then lose one more electron, which is why electrons on the right-hand side here become +2. That is what is referred to as the second ionization energy. It's about 1445 kilojoules. Then magnesium with a +2 charge will perhaps lose another electron and become magnesium with a +3 charge. That is the third ionization energy. So let's talk about, will that happen? So if we look at magnesium, which is 12, its electron configuration is 1s2, 2s2, 2p6, and 3s2. When we look at the configuration for magnesium, these two electrons are its valence electrons, right? It's also group number 2 on the periodic table, which is those two electrons right there. These guys here are the core electrons. So what happens in terms of magnesium is magnesium will only make a +2 charge. It is group number 2. It will make a +2 charge. And why is that? Well, it is because it has two valence electrons, which means those valence electrons, as we were just talking about, are further away from the nucleus. They're not held as tightly, and they can be removed pretty easily. And we see that with the first electron that comes off. It's only about 735 kilojoules. But what we see is after we pull off the first electron, it does become significantly harder to remove the second electron. You need almost twice the amount of energy to pull off the next electron. Why is that? Well, what happens when we lose an electron, right? So we lose an electron, say this guy is neutral. When he loses an electron, the cation actually will become smaller. And the cation will become smaller than the neutral guy because think about the electrons, they're flying around on the outside. So when we lose some of those electrons, the electron cloud is sometimes referred to, becomes smaller. Because it becomes smaller, the outermost electrons, like the second valence electron, then finds itself moving closer to the nucleus and closer to that positive charge, which means that second electron that you're trying to take off in this case is going to be held tighter because it has now just moved closer to the nucleus. And you can see here, it now requires almost twice the amount of energy to take off that second electron after the first one has been popped off. So what happens when you pop off that second one? Well, you pop off that second one, you now got a +12 charge happening from the nucleus, right? Because the protons don't change. But now you got those 10 electrons that are left that have now become closer to the nucleus, right? All those electrons flying around this area have now really contracted and coming closer to the nucleus. We now are into our core electrons, which are started out close to the nucleus, are now even closer to the nucleus and this +12 charge, which means you not only need to double the energy, you then need to go about 7 times more energy to try to pull off another electron. And in normal situations does not happen because now we're into our core electrons, right? After we remove those 2 electrons, we have now jumped into our core electrons. Every time an electron pops off, the overall electron cloud gets smaller, bringing whatever electrons were there even closer to that nucleus, which now has a much higher positive charge than negative charge, and going to hold those electrons in a lot stronger. So ionization energy and the idea of sort of core electrons and the shrinking of the overall size plays a very important effect as to how many electrons are typically lost by certain elements. And in the case of magnesium, typically elements will lose their valence electrons. Once you start dipping into the core electrons, because of in order to get to those core electrons, you have to lose the valence electrons, and everybody shrinks down in terms of size. Those core electrons are held extremely, extremely tight, are very strong because of that positive charge, and they typically are not removed. And that's why, we kind of stop with our representative elements in terms of electrons once we reach those valence electrons sort of leaving. Any questions on that there? Okay. So that is a very typical trend that we typically see when we talk about ionization energy. Is we typically do see it in general when we talk about ionization energy. It increases as we go to the right, and it decreases as we go left and down. So in general, as we go across the period from left to right, the first ionization energy increases. And that's a couple reasons why, electrons we basically have the buildup. So if you look at the atomic number as you go to the right on the periodic table, it's much higher numbers than on the left. The atomic number is the number of protons, which means, we have a much larger positive charge happening on the right-hand side of the periodic table in terms of the nucleus, which is in general going to bring everybody in closer to them in terms of electrons. So overall, because of that larger positive charge, because of the higher atomic number going to the right, everybody gets condensed in. And what that means is even the furthest electrons, even your furthest valence electrons, will find themselves closer in because of that higher positive charge, which means that they are going to be held tighter because the effective nuclear charge is still larger than it would be to the left, and it's going to take more energy to remove those electrons. And vice versa, as you go the opposite way on the periodic table, the atomic number is smaller, which means it's not going to bring those outer electrons in as much, and they won't be held as tightly, and it takes less in terms of ionization energy. And that's sort of, why we see a decrease as we go down a group, sort of as well. Here's just a chart, periods 2, 3, 4, and so forth on the periodic table. But the general trend we see is ionization energy will start to decrease as we go down a group and increase as we go across a period. So going across the period in better shot, I think. Right? So explain why the graph on ionization energy versus atomic number is not linear. It's not linear because of electron repulsions. Remember, although we're talking about electrons and stuff sharing the same space, there's still an aspect of they don't really want to be near each other because they are the same charge. And that's what electron repulsion means. Again, negative and negative things near each other. But in certain cases, as we've talked about or will talk about, even though things are the same charge, they can't really escape each other. So they have to kind of find a happy medium. And that's why we sort of see that weird sort of line where it kind of goes up and down rather than just a nice vertical arrangement. Are there exceptions? There are some exceptions in terms of, that general trend. But you don't have to worry too much about exceptions in terms of this class. You can just remember the general trend, and you probably would be okay in most cases for anything that you would need in terms of ionization energy. So which atom would require more energy to remove an electron, and why? So if we think about our sodium versus chlorine, they are in the same period on the periodic table. So if you just think about the general trend and a very badly drawn periodic table, sodium and chlorine are really in the same sort of group. Sorry, the same period on the periodic table, not group, but period. And we see that chlorine is further to the right. And remember, ionization energy increases as we go this way and decreases as we go that way, which means the chlorine should require more energy to remove an electron than the sodium. Again, chlorine hanging out with a positive 17 nucleus sodium hanging out with a positive 11 nucleus. So remember, just in general, even those outer electrons are going to be closer to the nucleus because of that positive 17 charge, while over here, those outer electrons will be a little bit further away from the nucleus and not held as tightly. So these guys, because they're closer to nucleus, requires more energy and has a higher ionization energy, and we would expect chlorine to be higher in that sense. Now, which atom would require more energy to remove an electron? So here, looking at lithium and cesium, again, these guys are actually in the same group on the periodic table, lithium and cesium here. And remember, our general trend increase in terms of ionization energy that way, decreases as you go this way. So we would expect our lithium here to require more energy to remove that electron than our cesium, because the outer electron is closer to the nucleus than the guy on the bottom. So the idea here is between lithium and cesium, the lithium is 1s2, 2s1. So there's only a total of 3 electrons total. So on average, you know, we're talking about electrons in the second energy level versus cesium, which is way down there, and we got electrons like in the 6th energy level. So on average, those electrons are going to be further away from the nucleus and not held as tightly. So which one would have the larger second ionization energy? Would it be lithium or would it be beryllium? So what do we mean by this? So if we think about lithium and we think about beryllium, they are neighbors to each other on the periodic table. We have lithium and we have beryllium, lithium being 3, beryllium being 4. So let's think about sort of the electron configuration for each of these. So lithium is again 1s2, 2s1, and beryllium here would be 1s2, 2s2. So second ionization energy would be the energy associated with losing 2 electrons. So we would talk about lithium would lose the first electron. That would be our first ionization energy. Then lithium with a +1 potentially would lose a second electron. That would be the second ionization energy. As opposed to if we look at beryllium, beryllium would lose 1 electron, being the first ionization energy. And beryllium then would drop off a second electron there, or our second ionization energy. Well, let's think about what this does in terms of electrons. As we've talked about before, when we look at lithium, which is group 1, it has 1 valence electron, right? Which is this valence electron. When we talk about beryllium, which is group number 2, remember valence electrons equals the group number, which means it has 2 valence electrons. So if we go to lithium, when it loses its first electron, it is actually the valence electron. Then what it would want to do to lose its second electron is it now would be into core electrons, which means, as we've just been talking about, probably should be a very big amount of energy. Remember that when we get into those core electrons, it's an enormous amount of energy. Usually doesn't happen. When we look at beryllium, loses the first electron, which would be here, loses the second electron, which would be here, and both of those are still its valence electrons. So although the ionization energy will increase as we go from here to here, it will still be smaller than the second ionization energy that we see here, because here we're getting into core electrons. And usually, again, will not take place in the case of lithium. And because it's going to be a really high number, we would expect lithium to have a much higher second ionization energy than beryllium, because beryllium is still in its valence electrons at that point, and would not require as high of energy than lithium would. Any questions on that there? So here's a chart of ionization energy, and this is 1 through 7. So it's first ionization energy. So basically first electron, second electron, third electron coming off, fourth electron, and so forth. And what we see is what we talked about. This is sodium, magnesium, aluminum. So this is going across period 3 of your periodic table. So going kind of left to right across. And what we see is as we go from left side of the periodic table to the right side of the periodic table, we see a very much increase typically in the ionization energy. So the general trend, not perfect as you can see, obviously, but the general trend as we go again left to right on the periodic table is our ionization energy is increasing. And if you go the opposite direction, it's decreasing. Again, going from right to left is decreasing, and also going down a group is decreasing. The other thing that we see is as we go from the first electron jumping off to the second electron, to even the third electron, to the fourth electron, we do see is as you continuously take off electrons, again, the overall size of everybody's going to shrink. And those electrons are going to be held tighter, which means it's going to take more energy to remove them. If you're removing another one, it's going to shrink, going to be more energy to remove it. So the general trend that we see is as we go from first ionization energy to second to third, we see an increase in the ionization energy, meaning it's harder to remove an electron once you've already removed one, and it gets harder and harder every time you keep removing an electron. And we also see on this chart a tremendous jump in the energy required to get yourself into the core electrons. So for example, sodium, which is 1s2, 2s2, 2p6, 3s1. Sodium has only one valence electron, which is the 3s, which takes this much energy to remove it. Now you want to go into the core electrons for sodium. You need about 10 times or tenfold increase in the energy. Again, does not typically happen at that point. Here's our magnesium. We talked about big jump to try to remove those electrons in the core electrons. Here's aluminum, which makes a +3 charge in most cases, an enormous amount of jump to try to remove those electrons. And you can see that once you sort of hit those electrons, those core electrons, it's very, very hard to obviously remove those, and it typically does not happen. So that's why when we think about something like sodium, it's pretty much known to have a fixed charge of +1 because of that. Also, something like magnesium has a fixed charge of +2 and so forth. Aluminum sort of a fixed charge of +3. And we see just in general, as we sort of travel over to our non-metal sort of side, very, very high numbers even to remove the first electron, which is why typically speaking, our non-metals don't lose electrons, because it takes a lot of energy even to remove that first one, versus on the other side. Another important trend is one which is known as electron affinity. And if you have an affinity for something, it means that you typically like something. And electron affinity is the energy change that occurs when we gain an electron. So if you think about ionization energy, which is what we've been talking about, that's pretty much what happens when we lose electrons. And when we lose electrons, we become positively charged. Now, when we talk about the energy change when we gain electrons, that is typically what occurs when we make an anion, which is negatively charged when we gain electrons. So when we talk about electron affinity, we oftentimes talk about it in the sense of we are making anions as opposed to in the sense of making cations with ionization energy. General trend is in terms of electron affinity, and again, not 100% perfectly trended, but in general, it increases as we go to the right and decreases as we go to the left. So things typically, as you go up and to the right, have a high electron affinity, which means that they pretty much like electrons and will gain electrons. guys to the left there typically will lose electrons and become positively charged. Another important sort of trend is atomic size. And what we see in terms of atomic size is based on some of these trends that we've been talking about, we do see that, you know, as you go up and to the right on the periodic table, we have things that pretty much have very high ionization energy, which means they typically don't want to lose electrons. They have high electron affinity, which means they kind of like electrons. And they also end up being very small as you go across. So the general trend is as we go kind of from right to left on the periodic table, size decreases as we go to the right and increases as we go to the left. So things get much, much smaller as you go to the right. Again, with that buildup of protons going to bring even those outer electrons in closer because of the higher positive charge, given the overall size of that guy being smaller as you go up to the right, and again, larger as you go down to the left. In addition, the few things we talked about in terms of charges is the cation is typically smaller than the neutral guy, and the anion is larger than the neutral guy. So when something gains an electron, obviously they add it to their electron sort of cloud. Electron cloud gets larger, and the overall size of the anion versus the neutral guy does sort of increase as you do that. And let's take a look at a picture here to sort of summarize some of the stuff that we talked about. Here's our size picture. So you can see that as you go to the right, the size of the atom gets smaller overall, which means those electrons are going to be held tighter and so forth. Another really important sort of trend to sort of add to our lists here to finish up our trends and is what is known as electronegativity. Electronegativity is different than electron affinity. Electron affinity is talking about the energy change that occurs when somebody gains an electron. Electronegativity is the ability of an atom to bring electrons towards itself or attract electrons towards itself. When we look at the periodic table, it increases as we go this way, with fluorine being the most electronegative element, and decreases as we go down. So if we think about sort of all of the trends that we just talked about here, just to kind of wrap this up here, all of the trends that we just talked about, which is as you go to the right on the periodic table, ionization energy increases. As you go down, it decreases. As you go to the right on the periodic table, size decreases. And as you go down, size increases. As you go to the right on the periodic table, electron affinity increases and decreases as you go down. As you go to the right on the periodic table, electronegativity increases and goes down on the periodic table. What does all those things mean? All those things mean is when we go up and to the right on the periodic table, pretty much that is where we find our nonmetals. And what happens with our nonmetals is up and to the right, we have things that have very high ionization energy, which means it takes a lot of energy to try to remove electrons. We have things that are very small, which means they're going to hold those electrons really tightly, which is why it takes a lot of energy to try to remove them. And not only that, they're going to hold on to their electrons because they have a high electron affinity, but in addition, they're going to go, I kind of want electrons as well. They're going to bring electrons towards themselves because they have a high electronegativity. All those things basically add up to what we know about nonmetals, which is they typically will gain electrons rather than lose electrons and become anions, are negatively charged. And vice versa, if we kind of go bottom left of the periodic table, we have things that have a much larger size, which means the outer electrons are not held as tightly. That means that you don't need a lot of energy to remove those electrons, so small ionization energy. They also have a small electron affinity, which means they're not really like, happy about gaining electrons. And they have a very small electronegativity, which means they're not really interested in bringing electrons towards themselves. All of those things come together for what we know about down and to the right on the periodic table. These guys are larger. They don't hold their electrons as tightly. These are the guys that typically will make cations in those situations, which are positively charged ions, and lose those electrons. And that's really the basis of ionic compounds. Metals, because of all those properties, typically will give up those electrons because they really are not interested in holding on to them. Non-metals, when they're near metals, are like, cool, I'll take the electron, and they want to gain those electrons. And now we have a positive guy and a negative guy, which can make an ionic compound and sort of come together. Any questions on those sort of trends? Okay, so we're actually almost done. So what I'm going to do is I think we'll lay it up here for now. We'll finish it maybe after the quiz.